All right, everyone, you've spent countless hours with the textbooks, right? You've seen those beautiful, perfect circuits on the page. But let me tell you, as someone who's been doing this for 25 years, when you step out of the classroom and into the lab, that clean, perfect world gets messy, fast. So in this explainer, we're going to bridge that gap. We're going to talk about how to take that ideal theory you've learned and build something that doesn't just work on a simulator, but actually survives and thrives out in the real world. So, here's our game plan for today. First, we're going to move beyond that perfect ideal switch. Then, we'll tackle the biggest problem that comes from that, heat. After that, we'll dig into the very real dangers of the switching process itself. Next up, we'll talk about the critical importance of staying within the limits of your components. And finally, we'll wrap it all up into what I call the designer's mindset. Okay, let's get right into it. Section 1, Beyond the Ideal Switch. You know, in your first circuits class, everything is simple. But this is where theory smacks right into the hard wall of reality. And this slide just lays it all out, doesn't it? On the one hand, you've got the ideal switch from your textbook. It's a dream, right? Zero power loss. It switches in literally no time, and it has no limits whatsoever. But then there's the real world. The components we actually use. Our MOSFETs, our IGBTs, well, they're a different story. They have losses that create heat. They have real, finite switching times, and they have very, very strict operational limits. You push them past those limits, and boom, catastrophic failure. Honestly, pretty much every problem we're going to talk about today comes from these three simple but crucial differences. Okay, so that brings us to our first major headache. Section 2, the problem of heat. Because every single one of those real-world imperfections, well, it generates heat. And let me tell you, heat is the #1 killer of electronics, period. And this quote from Rashid really hits the nail on the head. It's not some abstract concept. It's just simple physics. You have some voltage across your device and some current flowing through it. Well, that V times I product is power, and that power becomes heat. Our entire job as designers is to figure out how to get that heat away from the device before it literally cooks itself from the inside out. So how do we manage all this heat? Well, first, we have to understand its journey out of the device. And we do that with a concept called thermal resistance. Just think of it like, well, resistance to heat flow. It's a series of roadblocks. You've got one barrier from the tiny silicon chip itself, we call that the junction, to the plastic or metal case. Then another from the case to the heat sink you bolted onto. And then a final one from the heat sink out into the air. Our job is to make that whole path as easy as possible, to lower the total resistance. And this is where it gets really cool. We can actually model this whole heat flow problem just like an electrical circuit, something you all already know how to solve. In this analogy, the heat, which is power, acts like current. The temperature difference from the hot chip to the cool air acts like voltage. And those thermal resistances we just talked about, you guessed it, they're just like resistors. All of a sudden, we can use a version of Ohm's law to figure out exactly how hot the core of our device is going to get. It's a brilliant shortcut. And here's the solution in the real world, the heat sink. We literally bolt our power device onto one of these big chunks of aluminum. Why? Look at all those fins and crazy shapes. That's all designed for one single reason, to create a massive amount of surface area. More surface area means more contact with the air, and that gives the heat an easy escape route, letting it just radiate and convect away safely. Okay, so we've got a handle on the heat when the switch is just sitting there, either on or off. But what about that moment in between, the actual act of switching? That brings us to our next big problem, the dangers of switching. Because that transition, it's not instant, and it's one of the most stressful moments for any component. Now take a close look at these waveforms. When the switch is off, you've got high voltage but zero current, no power loss. When it's on, you've got high current but almost zero voltage. Again, minimal power loss. But look at that little crossover region. That's the danger zone. For a split second, both the voltage and the current are high at the same time. And what's V times I? Power. This creates a huge spike of power dissipation, a burst of heat every single time you switch. If you're switching thousands of times a second, these switching losses can become your #1 source of heat. So you might be thinking, okay, professor, I get it. Slow switching is bad. The solution must be to switch as fast as humanly possible, right? Well, that's a great thought, but it leads to a really important question. What happens if these voltage and current changes are too fast? And the answer is a huge, emphatic yes. It can be a massive problem. This is where we get into these critical terms, DIDT and DVDT. That's just a fancy way of saying rate of change of current and rate of change of voltage. See, every real circuit has tiny, unwanted bits of inductance and capacitance. If you change the current too fast, a high DIDT, that stray inductance can create a gigantic voltage spike that will kill your device. And if you change the voltage too fast, a high DVDT, you can accidentally turn on other components in your circuit. These are hard limits, right in the datasheet, and you have to respect them. Which brings us to probably the most fundamental rule of all. Section 4, staying within the limits. Every component you ever use will have a datasheet. Think of it as the component's Bible. It tells you exactly what it can and cannot do. Your job as an engineer is to know those limits inside and out and design your circuit so it never pushes the component past its breaking point. And you can't just think about max voltage and max current as two separate numbers. They're related. That's where the safe operating area, or SOA chart, comes in. The manufacturer gives you this graph that defines every possible combination of voltage and current where the device is safe. If your operating point is anywhere inside that boundary, you're good. But if it drifts outside, even for a microsecond, you're risking an instant and sometimes pretty spectacular failure. Okay, but let's be realistic. Things go wrong. A wire shorts out, a motor stalls. What happens then? A fault can cause a massive current spike that throws your device way, way outside its SOA. So how do we protect a device when that happens? How do we plan for the unexpected? The answer is you plan for a sacrifice, and that sacrifice is the humble fuse. But you can't just grab any old fuse. You have to be strategic. You need to look at a rating called I squared T. That's I squared T. It basically represents the total amount of thermal energy a device can handle before it's destroyed. The rule is simple, but it's absolutely critical. The I squared T rating of your fuse must be less than the I squared T rating of your semiconductor. That way, when a fault happens, the fuse blows first, saving your much more expensive power transistor. Okay, let's pull all of this together now. This isn't just a list of random things to worry about. It's a way of thinking. It's a mindset that every good power electronics designer has. A checklist for survival, if you will. And this is it. This is the checklist you should run through in your head for every single design. Number 1, quantify your power losses. You can't fight an enemy you can't see, so calculate the heat. 2, design the thermal solution. Pick the right heatsink. 3, analyze your switching stress. Check your DIDT and DVDT. Don't get lazy on this. 4, implement protection. Choose the right fuse. And finally, number 5, verify your operation within the SOA. Under all conditions, start up full load. Make sure you're staying within those safe limits. So there you have it. You know the theory from the books, you can solve the equations, but the real question is this: are you ready to build something that lasts? Because that, right there, is what separates a student from a professional engineer. It's not just about getting the circuit to work. It's about having the foresight to build something robust enough to survive the real world. That is the real challenge, and honestly the real art of what we do.